you're not doing something on the basis for the three-dimensional column space. You're literally nothing. Here's the zero vector of this class. I don't know. How's it make you feel? I think you turned too many pages.
Pages. I remember I like, but it's just like one.
You have to go into arguments on Mars. Here, all comes out an hour before this.
No, I'm always on my phone for like 2 hours. It's always like easy.
Mr. Smith, is our project going to be a major grade?
It's going to be in that category, yeah. It'll be worth half of a test. You'll basically.
Okay, thanks.
That's great. All right, guys, we have a very short lesson today, so we can do that, finish it. When we're done, don't forget you have a problem set due today. So if you haven't finished that and gotten that turned in, you could work on that. You could work on something for another class, or you could just take a break and finish it later or whatever. But yeah, pretty short lesson, so that's a good thing. And all right. So today we're looking at what are called similar matrices. Get this up here. Yep. Similar matrices. These are matrices that are similar. They have some things in common, but they are not the same, which is why we call them similar and not the same matrix. So we are basically going to go over how we find them and what are some of the properties that make them similar today. And then we'll see these come back up in some lessons soon as well. So first thing is similar matrices have the same eigenvalues. And we've actually then seen a set of similar matrices very recently. In the last few lessons, A and our matrix capital lambda are similar. From A equals S inverse, S lambda S inverse. Okay, A has eigenvalues lambda 1 and lambda 2 or whatever, and then we put those as diagonal entries of our capital lambda, so its eigenvalues are the same, right? Because in a diagonal we can just take the eigenvalues off the diagonal. So those two things have the same eigenvalues and they are similar matrices. And in fact, this is very similar to the definition of similar matrices, other than what we use for S here is very specific. It's the eigenvectors of A. If we put in other things there, we will get other similar matrices. So if we put something other than eigenvectors there, if we just put random other numbers in there, we'll get a new set of similar matrices. So the definition is just if I take A and I multiply on one side by M inverse, on the other side by M, I will get another matrix that has the same eigenvalues as A, which is what we call a similar matrix. So B will be similar to A if there's some matrix M where B is equal to M inverse AM. Okay, and M just has to be invertible. So you could make up any M you want and get another similar matrix to A. By just putting an M there. It just has to be invertible so that you could multiply by M inverse. Okay, this means A is also similar to B. right? We could show that by definition pretty easily. If B equals M inverse AM, I can multiply from the left by M on both sides of the equation. I can multiply from the right by M inverse on both sides of the equation. And so A equals M B M inverse, which is not quite the same as the definition. But if we just let N equal M inverse, okay, there, let's say M inverse is a matrix, then this is N inverse B N, which means by definition, A is also similar to B, because there is some matrix N that I could do N inverse B N and get A. So either direction, it's the same. It's just that you wouldn't use the same M. If I were trying to show B is similar to A or A is similar to B, the matrix will be different when you set up your equation, but the fact will still be the same. If B is similar to A will be similar to B as well. And generally, we're not trying to find M. We're either given an M and say, use this M to get a similar matrix, or we're coming up with an M to get a similar matrix that we want. Like, again, for diagonalizing, we choose an M that is made of eigenvectors to make it diagonalizable, to create a matrix that we can multiply quickly a lot of times. We could choose different M's to get different results, but we're not usually going backwards. Like, here's two similar matrices. What M did we use? We're not usually looking for it that way. That would be really difficult. So we're usually looking more for, are these things similar, or create one using this M or something like that. So here we have an A and we have an M, and we're going to find B, a similar matrix to A. So B will be M inverse times A times M, which means we need the inverse of M. So we find the determinant. Determinant is 1 minus 0. So 1. We switch the values on the main diagonal, which are 1s, so those don't really do anything. And then switch the sign on the other diagonal, so I'll have a 0 and a -1. And so to get B, we do M inverse. So 1, 0, -1, 1 times A, 1, 2, 0, 3 times M, which is 1, 0, 1, 1. If I multiply the first two, I'll have 1, 0 times 1, 0 is 1. 1, 0 times 2, 3 is 2. -1, 1 times 1, 0 is -1. And then -1, 1 times 2, 3 will be -2 plus 3, which is 1. And then if I multiply that one with the third, I'll have 1, 2 times 1, 1 is 3, 1 plus 2. 1, 2 times 0, 1 will be 2. -1, 1 times 1, 1 will be -1 plus 1, which is 0. And then -1, 1 times 0, 1 is 1. And so we have a similar matrix. It is just a coincidence that it's basically flipped over the opposite diagonal, right? We got almost the same matrix here. That's just because of the M we use. That won't always happen. Okay, but what will always happen is the eigenvalues will be the same. And these two, it's easy to identify. The eigenvalues of A are here. And the eigenvalues of B are here. And notice that they are the same. Okay, and that should always happen no matter what M you choose. It won't necessarily come out upper triangular or lower triangular or diagonal or something, but you will always have the same eigenvalues, no matter what M you choose. Okay, a careful choice of M could make different things easier to deal with. And again, we'll kind of see some of this later. Soon we're talking about like changing a basis or transformations, and similar matrices can help in some of those situations. We've already seen, again, the diagonalization. That's a set of similar matrices, and that helps us multiply a lot. We could need upper triangular or lower triangular or other things, but we get a diagonal matrix when we use eigenvectors, okay, which is what S is made of, is eigenvectors. If we use other things, we'll get different results there. Okay, but we could even do things like, say I wanted something similar to 2, 0, 0, 5, or even something with the eigenvalues of 2 and 5, either way. But I want eigenvectors 1, 2, and 3, -5. Well, then I could come up with that matrix by taking my eigenvectors 1, 2, and 3, -5, putting them as columns, taking this 2, 0, 0, 5, and then taking the inverse here. Multiply that out, you will have a similar matrix to A, meaning it will also have eigenvalues 2 and 5. I mean, a similar matrix to 2, 0, 0, 5, meaning it will have eigenvalues 2 and 5, but it will have eigenvectors 1, 2, and 3, 5. So we could kind of choose M's to get what we want in different ways. This one would be a way to construct a matrix with eigenvalues that I want and eigenvectors that I want. All right, so another example, we already know that if A is like 0.5, 0.5, 0.5, we could find that capital lambda by doing S inverse AS. So again, notice this is basically the same as our definition of similar matrices. It's just that we're choosing a specific M that's made of eigenvectors. So with A, that's a Markov matrix, meaning one of our eigenvalues is 1, because for Markov matrices, one of them is always 1. The second one we can find by taking the trace, -1. Well, the trace here is 1/2 plus 1/2, which is 1. -1 is 0. So we have our 2 eigenvalues there. So our capital lambda, notice that's what we put here, right, is our 2 eigenvalues, 1 and 0. Those two are similar. They are similar by definition, but they're also similar, having the same eigenvalues there. But again, we could use any M we want as long as it's invertible. It doesn't have to be S's, and we could get other types of similar matrices. So here, if we use that same M we used before, the inverse was 1, 0, -1, 1, times A, which is 0.5, 0.5, 0.5, 0.5, times M. We could get another similar matrix that's similar to both A and capital lambda. It'll be a different one that's similar to both. So again, I'm going to multiply the first two here. 1, 0 times 0.5, 0.5 is going to be 0.5. 1, 0 times 0.5 and 0.5 is 0.5. -1, 1 times 0.5, 0.5 will be -0.5 plus 0.5, which is 0. And then the same thing for the second column. Okay, 0.5 times 1, 1 is 0.5 plus 0.5, which is 1. 0.5, 0.5 times 0, 1 is 0.5. And then 0, 0 times anything is going to be 0. So again, we should see, here's the eigenvalues of B, which are the same as the eigenvalues of A and the same as the eigenvalues of capital lambda, 1, 0. These three are all similar matrices. and they might be useful for different things. Like A is a Markov matrix, and B is not. Okay, lambda is technically a Markov. No, lambda is not either, because lambda doesn't, the columns don't add up to 1. So they're not the same. They don't have everything in common, but they do have the same eigenvalues, and they could be used for different purposes. But we could basically generate as many of these things as we want just by multiplying by whatever m is invertible that we want and getting more similar matrices. Okay, not only do they have the same eigenvalues, but that's one way to identify if you're looking at similar matrices, is if they have the same distinct eigenvalues, they are similar. Distinct meaning different. Okay, they can't be repeated eigenvalues. So, for example, like 1, 0, 0, 1, the identity, and 1, 1, 0, 1 are not similar. Okay, they have the same eigenvalues, 1 and 1. But repeated eigenvalues sometimes are going to let you have different eigenvectors and sometimes they aren't. And so that's not a good way to identify similar matrices. But as long as they're different, like 1 and 2 are my eigenvalues, you will have different eigenvectors. They will be similar. So for example, here A and B are similar. I don't know what the m is that got me from one to the other. They can be, but it's not guaranteed. Yeah, if they have the same eigenvalues and the eigenvalues are the same as each other, like 1 and 1, it's possible that they're similar, but it's not guaranteed. They will be if they also have distinct eigenvectors. But like the identity and that other one don't have the same distinct eigenvectors. All right, so eigenvectors of A, again, are 1 and 5. Eigenvectors of B are also 1 and 5, which means A and B are similar, which does mean some m exists such that B equals m inverse A m. We just don't know what m is, but it does exist. There is some invertible matrix that would make that happen. But again, usually we're not super interested in what m is. We usually have the m already, or we know a specific m we want to use to make the result that we're looking for. So we aren't solving for m. We're generally more interested in, are the matrices similar? So there's one way to figure that out. Okay, things that are the same in matrices mostly are based on the eigenvalues being the same. So they have the same eigenvalues, which is what we've been talking about. They'll have the same trace, because remember, the trace is the sum of the eigenvalues. Which means if we have the same eigenvalues, we will have the same trace, because you'll add those eigenvalues up in both and they'll be the same. The determinant is similar. Remember, that's the product of the eigenvalues. So as long as you have the same eigenvalues, they'll have the same product, they'll have the same determinant. You'll have the same rank, which means you have the same number of vectors and a basis for your 4 subspaces. You'll have the same number of pivots, the same number of free variables, all that stuff. And you'll have the same number of independent eigenvectors. All right. Notice that it says you have the same number of eigenvectors, but you won't have the same eigenvectors. They will be different. But if we know an eigenvector of A and B is similar to A, M inverse X will be an eigenvector of B. So they will be different, But if we know M and we know an eigenvector of one, we usually can find the eigenvector of the other. And again, this is not super hard to show. If we start with that definition of similarity, if I multiply both sides by the inverse of M on the right, and then I multiply by X, X being that eigenvector. Okay, X is an eigenvector of A, meaning AX is equal to lambda X. And so we have B times M inverse X equals lambda times M inverse X. Remember, lambda is a constant, so I could just pull that out front. And this is the definition of eigenvectors. Is that B times that vector is just a multiple of that same vector. M inverse X is a vector. And notice it's the same multiple as AX was of X. It's lambda, the eigenvalue was the same eigenvalue, lambda. The vector is just different. It's not X, it's M inverse X is our eigenvector for B. The what? Eigenvector of A is X, eigenvector of B is M inverse times X. Yeah. This would be your eigenvector for B. Because notice you're getting a multiple of that same vector there. All right, things that are not the same. Okay, we just mentioned eigenvectors will not be the same. Your null space is not necessarily the same. Okay, when I say not the same, it's not like a rule. You could have the same null space, you could have the same column space, but it's not guaranteed. Okay, it's not something you know is going to happen. Okay, and really a lot of other things. They're not the same. So there's a lot of things they will not have in common with each other. So don't assume because they're similar that stuff's the same in there that we haven't necessarily shown or said here. So one of our previous examples is a good easy way to kind of show these things are not the same. If we go back up here to this one, okay, we have three similar matrices here, A, lambda, and B. And for example, like the column space of B is the x-axis, right? If we look at this, a basis for the column space would be 1, 0. You're not getting any y values from B. The whole second column, second row is zeros. So the basis for the column space would be 1, 0, the x-axis. Okay, same with capital lambda. Basis, x-axis. But if we go over to A, that is not the x-axis. That is the line y equals x. It is still the same dimension, right? Our rank is the same, which means we'll have the same dimensional column space. We just won't have the same column space necessarily. So lambda and B do, but A and B don't. Null space, same idea. Okay, the null space of B is basically going to be, what is that? 1/2 -1 would be your null space. The basis of lambda will be any multiple of 0, 1. And the basis of the null space of A will be 1, -1. Okay, those don't have the same null space. Some of them can have the same null space, some of them could have the same column space, but it's not guaranteed there. So we could kind of show a lot of examples where some of them are, some of them aren't, because it's not guaranteed. All right. If you're asked to see if two matrices are similar, I would find eigenvalues. Okay, unless you have a reason to, don't try to find M. Don't use the definition. Okay, just like most things that we do, the definition is usually the long, hard way of doing things. So I would not try to find M. I would find the eigenvalues. It's like A, they're right there. Eigenvalues are 2 and 6. For B, you could use determinants and trace or whatever, but we could just find the eigenvalues. So we have 16 minus 8 lambda plus lambda squared minus 4. So we have lambda squared minus 8 lambda plus 12 equals 0. So we have lambda minus 6 and lambda minus 2. So we have eigenvalues also 2 and 6. So A and B are similar. Okay, again, that means that M does exist. There is some M where B is just M inverse A M. A different M exists where A equals M inverse B M. But we don't necessarily need to find it. Okay, these matrices will have the same rank, which like in A, I can see the rank is 2, which means the rank of B is also 2. Okay, the determinant of A I can see is 12. The determinant of B is also going to be 12. The trace of A is 8. The trace of B is also 8. Those things should be the same. Not the determinant by itself. Yeah, the determinant itself's not enough, but in a 2x2, the determinant and the trace combined should be enough. In anything larger, that's not enough either. But they should be true also, but it's not enough to know that they're similar to just do one of those things. You'd want to do, well, I would do eigenvalues basically. All right, that's all that we have today. Again, if you haven't finished your problem set, you should get that done and turned in. And you guys have a good weekend, and I'll see you guys next week.
Thank you.
Have a good weekend.
You too.